Hello students. In this session, we will discuss numericals about mobility and resistivity and the conductivity in the semiconductor. Okay, so let me start with this numerical. In an N-type semiconductor at a temperature 300 Kelvin, the electron concentration varies linearly from 2 into 10 to the power 18 per centimeter cube to 5 into 10 to the power 17 per centimeter cube over a distance of 1.5 millimeter, and the diffusion current density is 360 ampere per centimeter square. Then find the mobility of electrons. Okay, so in this numerical, right, what we are given in the N-type semiconductor, when temperature is 300 Kelvin, the electron concentration varies linearly from 2 into 10 to the power 18 per centimeter cube to 5 into 10 to the power 17 per centimeter cube. Okay, so when electron concentration is varying, so it means diffusion current will flow, and the diffusion current density is given. It is 360 ampere per centimeter square. Then find the mobility of electrons. Okay, so when we draw the diagram of this semiconductor here, then this diffusion current density is varying from 2 into 10 to the power 18 per centimeter cube to 5 into 10 to the power 17 per centimeter cube, like this. Okay, over a distance of 1.5 millimeter. So diffusion current will flow, and the density of diffusion current, it is Q into dn. Dn is the diffusion constant, into dn over dx. Okay, so diffusion current density is given here 360 ampere per centimeter square. Charge is 1.6 into 10 raised to power minus 19 into dn. Dn is a diffusion constant, and dn over dx, it is given 5 into 10 to the power 17 minus 2 into 10 to the power 18 divided by over a distance of 1.5 millimeter. So we'll convert into the centimeter. So it is 1.5 into 10 to the power minus 1. So from here we will calculate the value of diffusion constant for electrons, and this is minus of 225. But diffusion constant is always positive, right? So diffusion constant will take, it is 225 centimeter square per second. Okay, and according to the Einstein's equation, dn is equal to mu n into Vt. So at room temperature, Vt is 26 millivolt, so mu n, it is dn by Vt, it is 225 by 26 into 10 raised to power minus 3. So this value comes as 8654 centimeter square per volt second. Okay, so in this question what we was given, we was given that dn over dx is a concentration gradient. Okay, so let me write here dn over dx, it is concentration gradient. Okay, and it was given in this question. It was given in this question 5 into 10 to the power 17 minus 2 into 10 to the power 18 over a distance of 1.5 millimeter, it means 1.5 into 10 raised to power minus 1. So this is dn over dx, which was given to us, right? So diffusion current, the formula of diffusion current, it is q into dn over dx. So we put here this concentration gradient, this is the value, and the dn is the diffusivity or diffusion constant, and q, it is 1.6 into 10 raised to power minus 19, and diffusion current density, it is given 360 ampere per centimeter square. So diffusion constant for electron comes as dn is equal to minus of 225, or when we take magnitude, so it is 225 centimeter square per second. Okay. So the next question is the mobility of electrons and holes in a silicon semiconductor are 0.125 meter square per volt second and 0.048 meter square per volt second. Determine conductivity of intrinsic silicon at a temperature 300 Kelvin. If intrinsic concentration Ni, it is 1.6 into 10 raised to power 16 per meter cube. When it is doped with 10 to the power 23 phosphorus atoms per meter cube, then determine equilibrium, hole concentration, and conductivity, and the position of Fermi level with respect to intrinsic level. Okay. So the first thing which it is asking, that it is an intrinsic conductivity, and the formula of intrinsic conductivity, it is Ni into Q into mu n plus mu p. So Ni, which is an intrinsic concentration, this value is 1.6 into 10 raised to power 16, as it is given here, and charge charge is 1.6 into 10 raised to power minus of 19, and mu n plus mu p, it is 0.125 plus 0.048. So intrinsic conductivity, when we solve, it is 0.4428 into 10 raised to power minus 3. Hi, good afternoon, Vaibhav. Right. So 0.4428 into 10 raised to power minus 3 mho per meter. This is our answer. Now when it is doped with phosphorus atoms, then n-type semiconductor will be formed, and for that n-type semiconductor, hole concentration, it is Ni square by n according to mass action law. So Ni, it is given 1.6 into 10 raised to power 16, its whole square by 10 to the power 23. So it is 2.56 into 10 to the power 9 per meter cube. So the conductivity of n-type semiconductor, it is Nd into Q into mu n. So Nd is, it is given 10 to the power 23, charge, it is 1.6 into 10 raised to power minus of 19, and mu n, it is 0.125. Okay. So this conductivity of n-type semiconductor, it is 2 into 10 cube mho per meter. So it is also asking the shift in the Fermi level, and the formula of shift, it is kT ln Nd over Ni. Formula of shift, it is kT ln Nd over Ni. K is a Boltzmann constant, which is value 8.62 into 10 raised to power minus 5. and temperature is given 300 Kelvin, which is a room temperature. Ln Nd, it is 10 to the power 23 divided by Ni, it is 1.6 into 10 raised to power 16. So this is our answer, and the shift is 0.404 electron volt. And the next question is, find the energy. Fermi energy of silver is 8.8 into 10 raised to power minus 19 joule. Then calculate the velocity of the fastest moving electron in the silver at 0 Kelvin. Okay, so this is the question which is given, right? So Fermi energy formula is half of m V max square. Is it okay? So V max, it is under root of 2 EF by m. EF is the Fermi energy, so it is under root of 2 into 8.8 into 10 raised to power minus 19 upon m. It is 9.1 into 10 raised to power minus 31 kg. So V max, it is 1.4 into 10 raised to power 6 meter per second. So the next question is, what is the diffusion length of electron in a semiconductor? If the mobility of electron is mu n, it is 0.36 meter square per volt second, and the carrier lifetime tau n, it is 340 microsecond at room temperature, and thermal voltage is given 26 millivolt. So carrier lifetime is the time between generation and recombination process in which charge carrier will remain as a free charge carrier, है ना? And it is called as carrier lifetime. When when generation process occurs, then electron and hole pair generates, but eventually when electron has a tendency to recombine with the hole again, right? So after some time, both electron and hole again recombine, and they don't behave like a free charge carrier. So the time between generation and recombination process in which the electrons and holes will remain as a free charge carrier is called as carrier lifetime. And here is a length of diffusion, or it is also called as diffusion length. It is the average length traveled by charge carriers before recombination in the diffusion process. When diffusion process occurs, then continuously recombination takes place, right? Then when the recombination takes place, then the charge carrier will again not behave as a free charge carrier. So before the recombination, the average length traveled by any charge carrier is called as diffusion length, and the diffusion length, it is under root of d into tau. So according to our question, length of diffusion, it is under root of d into tau, and d is mu n into Vt into tau n. So mu n, it is a mobility of electron, it is 0.36 into Vt. Vt is 26 into 10 raised to power minus 3, and tau n, it is a carrier lifetime, it is 340 into 10 raised to power minus 6. Okay, so this answer is 1.78 millimeter. And the next question is, the electron concentration in a sample of uniformly doped n-type silicon at 300 Kelvin varies linearly from 10 to the power 17 per centimeter cube at x is equal to 0 to 6 into 10 raised to power 16 per centimeter cube at x is equal to 2 micrometer. If diffusion constant dn is 35 centimeter square per second, then calculate diffusion current density for electron. So diffusion current density for electron, it is q into dn over dx. So q is a charge. It is 1.6 into 10 raised to power minus of 19 into dn. Dn is a diffusion constant. It is 35 into dn over dx. It is 6 into 10 raised to power 16 minus 10 raised to power 17 divided by 2 into 10 raised to power minus 4. Because it's a given, it's a 2 millimeter. These electrons are diffusing at the distance of 2 millimeter, 2 micrometer, right? Okay. So this answer comes as minus of 1120 ampere per centimeter square. Okay. So next question is, a heavily doped n-type semiconductor has following data. Hole electron mobility ratio is 0.4. Doping concentration is 4.2 into 10 to the power 8 atoms per meter cube. Intrinsic concentration, it is 1.5 into 10 to the power 4 atoms per meter cube. Then calculate the ratio of conductance of n-type semiconductor to that of the intrinsic semiconductor. Okay. So what we want to calculate, we have to calculate the ratio of conductance. It is Z1 over Z2. It is also equal to sigma 1 over sigma 2. So it is NdQ into mu n divided by NiQ into mu n plus mu p. Right? Because first semiconductor is n-type and second semiconductor is intrinsic. So we want to calculate their ratio, conductivity ratio. Conductance ratio is equal to conductivity ratio here, right? So Q and Q will cancel each other. So Nd upon, and we will divide it with mu n. So Nd upon Ni 1 plus mu p by mu n. So Nd, it is 4.2 into 10 to the power 8 divided by Ni, it is 1.5 into 10 raised to power 4 and 1 plus 0.4. So sigma n upon sigma I, it is 20,000. Next question is, a silicon sample A is doped with 10 to the power 18 atoms per centimeter cube of boron atom, and and sample B of identical dimension is doped with 10 to the power 18 atoms per centimeter cube of phosphorus atoms. And it is given mu n by mu p, it is 3, right? Mu n by mu p is given 3. Calculate sigma A by sigma B. Okay, so sigma A over sigma B. Sigma A, it is p q mu p, and sigma B is n q mu n, because first sample is doped with boron, so conductivity is p q mu p. Second sample is doped with phosphorus, so conductivity is n q mu n. So mu p by mu n, it is 1 by 3. Next question is, the dependence of the drift velocity of electron on the electric field in a semiconductor is shown in figure. The semiconductor has uniform electron concentration of N. It is 1 into 10 to the power 16 per centimeter cube. If a bias voltage of 5 volt is applied across 1 micrometer region of semiconductor, calculate resulting current density in kiloampere per centimeter square. And this graph is shown in figure here. So electric field versus VD graph is given. Initially it is a linear graph and then it is saturated. So we are given with the electric electric field. Voltage is given 5 volt and distance is given 10 to the power minus 6. So here electric field will be 5 into 10 to the power 6 volt per meter. When we calculate in volt per centimeter, so it is 5 into 10 to the power 4 volt per centimeter. So we have to calculate the drift velocity at this particular electric field, and the electric field is given 5 into 10 to the power 4 volt per centimeter. So according to this straight line, this is a line which is passing through origin. So it is y is equal to mx. M is a slope. So slope is 10 to the power 7 upon 5 into 10 raised to power 5 into e. So it is 10 raised to power 6 centimeter per second. This is drift velocity. So at electric field of 5 into 10 to the power 4, we are getting drift velocity of 10 to the power 6 centimeter per second. Okay, so the formula of J is a drift current density. The formula is sigma into E, and sigma is NQ mu N into E. So it is NQ into VD, because mu N into E is a VD. Here mu N into E is a drift velocity. So we'll put all the values. The value of N, which is a concentration of electron, it is 10 raised to power 16. Q is 1.6 into 10 raised to power minus 19. And VD is 10 raised to power 6. So J is 1.6 kiloampere per centimeter square. So this is the formula of, this is the answer of J. Let me solve some numericals about graded semiconductor. So the figure below shows the doping distribution in the p-type semiconductor. It's given here from 1 micrometer to 2 micrometer, and the concentration of holes, it is 10 to the power 14 to 10 to the power 16. Okay, calculate the magnitude of electric field in kilovolt per centimeter. So it is the formula of V2 minus V1, it is Vt ln P1 by P2. Here P1 is greater than P2. So V2 minus V1, it is 26 into 10 raised to power minus 3 ln P1 is 10 raised to power 16 by 10 to the power 14. So V2 minus V1 is here 26 into 10 raised to power minus 3 ln 100. So here when we solve V2 minus V1, it is 119.73 millivolt. So electric field which is equal to V2 minus V1, our x2 minus x1. So it is 119.73 millivolt. Our x2 minus x1, it is 2 micrometer minus 1 micrometer. So this is 1.19 kilovolt per centimeter. And the next question is, an N plus N plus a silicon device is fabricated with uniform and non-degenerate donor doping concentration of ND1 is 1 into 10 to the power 18 per centimeter cube and ND2 10 to the power 15 per centimeter cube, corresponding to N plus and N regions. Thermal voltage Vt is 25 millivolt and Ni, it is 1 into 10 to the power 10 per centimeter cube. Then what is the magnitude of built-in potential? So built-in potential VBI, it is Vt ln 10 to the power 18 by 10 to the power 15. So this potential, built-in potential, it is 0.173 volt. Okay, so built-in potential generated due to non-uniform doping, right? Let me solve the next question. In an N-type semiconductor at temperature 300 Kelvin, the electron concentration varies from 2 into 10 to the power 18 per centimeter cube to 5 into 10 to the power 17 per centimeter cube over a distance of 1.5 millimeter, and diffusion current density is 360 ampere per centimeter square. Then find the mobility of electrons. So here concentration gradient is given dn over dx. Concentration gradient, it is 5 into 10 to the power 17. It is the final electron concentration minus initial electron concentration. It is 10 to the power 18 divided by 1.5 millimeter. So this is called as concentration gradient. So diffusion current density, it is Q into dn over dx. So diffusion current density is given 360 ampere per centimeter square. Q is 1.6 into 10 raised to power minus 19 into dn over dx. So it is 5 into 10 raised to power 17 minus 2 into 10 raised to power 18 over 1.5 millimeter stands. So diffusion constant, so Diffusion constant is taken as positive number, so it is 225 centimeter square per second. And diffusion constant, it is mobility into Vt. As we know the formula, dn by mu n, it is equal to Vt. So Vt is 26 millivolt, so mu n, it is dn by Vt. dn is 225 divided by Vt is 26 into 10 raised to power minus 3. So this answer is 8654 centimeter square per. Next question is, the mobility of electrons and holes in a silicon semiconductor are 0.125 meter square per volt second and 0.048 meter square per volt second. Determine conductivity of intrinsic silicon at a temperature 300 Kelvin if Ni is 1.6 into 10 raised to power 16 per meter cube. When it is doped with 10 to the power 23 phosphorus atoms per meter cube, then determine equilibrium hole concentration and conductivity and position of Fermi level with respect to intrinsic level. So the formula of intrinsic conductivity, it is Niq into mu n plus mu p. Ni is the intrinsic concentration, which is given as 1.6 into 10 raised to power 16. Charge is 1.6 into 10 raised to power minus 19 into mu n plus mu p. It is 0.125 plus 0.048. So intrinsic conductivity is 0.4428 into 10 to the power minus 3 mho per meter. So when it is doped with phosphorus atoms, then n-type semiconductor will be formed. So hole concentration is Ni square by n according to mass action law. So it is 1.6 into 10 raised to power 16 whole square by n. N is 10 to the power 23. So it is 2.56 into 10 to the power 9 per meter cube. Conductivity of n-type semiconductor, it is Nd into Q into mu n. Nd, it is donor ion concentration, which is given 10 to the power 23. And the charge is 1.6 into 10 raised to power minus 19 into mu n. Mu n is 0.125. So conductivity is 2 into 10 cube mho per meter. And the shift in the intrinsic shift in the Fermi level with respect to intrinsic semiconductor, it is kT ln Nd by Ni. K is Boltzmann constant. It is 8.62 into 10 raised to power minus 5 into 300 ln Nd over Ni. It is 10 to the power 23 over 1.6 into 10 raised to power 16. So the shift in the Fermi level. Okay, thank you. Right. So shift in the Fermi level, it is 0.404 electron volt. 0.404 electron volt, right? Okay, right. Next question is Fermi energy of silver. It is 8.8 into 10 raised to power minus 19 joule. Then calculate the velocity of fastest moving electron in the silver at 0 Kelvin. So Fermi energy, it is half of mv max square, right? So v max, it is under root of 2 EF by m. Two EF by m, right? Okay. So it is 2 into EF. EF is the Fermi energy. Fermi energy is given 8.8 into 10 raised to power minus 19 by m. M is the rest mass of electron. M is here the rest mass of electron. Okay. So when we solve here, then the maximum velocity, it is 1.4 into 10 raised to power 6 meter per second. And the next question is given, what is the diffusion length of electron in a semiconductor if mobility of electron is mu n is equal to 0.36 meter square per volt second, and the carrier lifetime tau n, it is 340 microsecond at room temperature. Thermal voltage is 26 millivolt. So let me understand what is carrier lifetime. Carrier lifetime is the time between generation and recombination process, in which charge carrier will remain as a free charge carrier. Okay, carrier lifetime, when it is a time between when generation process occurs, then electron and hole pair generates, right? But after some time electron again recombine with the holes, so that electron hole pair disappears at that time. Okay, so time between generation and recombination process, when the charge carriers exist as a free charge carrier, it is called as carrier lifetime. And the diffusion length, it is the average length traveled by the charge carrier before recombination. When diffusion process occurs, then charge carrier also recombines when minority charge carriers are injected in the extrinsic semiconductors. Then minority charge carrier diffuse in the semiconductor. Like this is a p-type semiconductor, and when we are injecting the electrons here, so electrons will continuously recombine with the holes in the p-type semiconductor, and their concentration will exponentially decrease with respect to distance. Okay, so diffusion length is, it is the average length traveled by the charge carriers before the recombination process. So L is under root of d into tau, and d is a diffusion constant, it is mu n into Vt, and it is tau n, right? So mu n is 0.36 into Vt. Vt is 26 into 10 raised to power minus 3, and tau n, it is a carrier lifetime, it is given 340 microsecond. So 340 into 10 raised to power minus 6. So this answer is 1.78 millimeter. Okay, and the next question is the electron concentration of uniformly doped n-type semiconductor at 300 Kelvin varies linearly from 10 to the power 17 per centimeter cube at x is equal to 0 to 6 into 10 raised to power 16 per centimeter cube at x is equal to 2 micrometer. Dn, which is a diffusion constant, it is 35 centimeter square per second. Then calculate diffusion current density for electrons. So the diffusion current density for electrons, it is q into dn over dx, right? So charge is 1.6 into 10 raised to power minus of 19 into diffusion constant is given 35 and dn over dx. Dn over dx, it is the change in concentration with respect to distance. So it is 6 into 10 raised to power 16 minus 10 to the power 17 divided by dx. Dx is 2 into 10 raised to power minus 4. So it is minus of 1120 ampere per centimeter square. A heavily doped n-type semiconductor has following data. hole electron mobility ratio is given 0.4. Okay, and the doping concentration is 4.2 into 10 to the power 8 atoms per meter cube. Intrinsic concentration is 1.5 into 10 to the power 4 atoms per meter cube. Then calculate the ratio of conductance of n-type semiconductor to that of the intrinsic semiconductor. So the ratio of conductance, it is equal to the ratio of conductivity sigma 1 to sigma 2. Now the first semiconductor is n-type and the second is intrinsic, so we have to take the ratio. So Nd q mu n, it is the conductivity of n-type semiconductor, and Ni q into mu n plus mu p, it is the conductivity of intrinsic semiconductor. So we will divide these two conductivities, and our answer is Nd upon Ni 1 plus mu p over mu n. So Nd is given 4.2 into 10 to the power 8 divided by Ni, it is 1.5 into 10 raised to power 4, 1 plus mu p by mu n, and mu p by mu n is given 0.4. So sigma n over sigma I, it is 20,000. Okay, is it clear? So next question is, a silicon sample A is doped with 10 to the power 18 atoms per centimeter cube of boron atom, and sample B of identical dimensions is doped with 10 to the power 18 atoms per centimeter cube of phosphorus atoms, right? So when we will dope with boron atoms, then the resultant semiconductor is p-type. When we will dope with phosphorus atom, then resultant semiconductor will be of n-type. And mobility ratio is also given mu n by mu p, it is equal to 3. Then we have to calculate sigma A over sigma B. Okay, so sigma A over sigma B, A type it is A semiconductor, it is of p type, so it is p q mu p, and B is a n type semiconductor, so n q mu n, but p and n both are equal, so p and n will cancel, q and q will cancel, so mu p over mu n, and mu p over mu n, it is 1 by 3. Next question is, the dependence of drift velocity of electron on electric field in a semiconductor is shown in the figure. The semiconductor has uniform electron concentration of n is equal to 1 into 10 to the power 16 per centimeter cube. If a bias voltage of 5 volt is applied across 1 micrometer region of semiconductor, then calculate resulting current density. Okay. So electric field, it is V by D, it is 5 volt by 10 to the power minus 6 meter. It is 5 into 10 to the power 6 volt per meter. When we calculate it in volt per centimeter, so it is 5 into 10 to the power 4 volt per centimeter. At this electric field, we have to calculate the value of mobility, right? So Vd, it is 10 to the power 7 upon 5 into 10 to the power 4 into E. It is the straight line equation, y is equal to mx. So from here we can calculate the value of Vd, it is 10 to the power 6 centimeter per second at electric field of 5 into 10 to the power 4, right? So the value of current density, it is J, it is sigma into E, and it is nq mu n into E, and mu n into E, it is a drift velocity Vd. So we can put here nq into Vd. So it is 10 to the power 16 into q, it is 1.6 into 10 raised to the power minus 19 into Vd is 10 to the power 6, right? So the value of current density, it is 1.6 kilo ampere per centimeter square. This is our answer. Let me solve some numericals for the graded semiconductor. Graded semiconductors are the semiconductor in which the concentration of charge carriers varies with respect to distance, hence diffusion current may flow. So let me solve one question which is of GATE exam as well, right? The figure below shows the doping distribution in the p-type semiconductor. So here is 10 to the power 14 per centimeter cube, it is a concentration of holes, and here it is a 10 to the power 16 per centimeter cube, it is a concentration of holes on this side, right? And this is a distance, and here it is given 1 micrometer, and here it is given 2 micrometer. So calculate the magnitude of electric field in the semiconductor due to non-uniform doping. So we know the value of V2 minus V1. V2 minus V1, it is Vt ln P1 by P2. It is given P1 is greater than P2. So V2 minus V1, it is 26 into 10 raised to power minus 3 ln 10 to the power 16 over 10 to the power 14. So it is 26 into 10 raised to power minus 3 ln 100. So V2 minus V1, it is 119.73 millivolt. So electric field is here 1.19 kilovolt per centimeter. So the next question is, an N plus N silicon device is fabricated with uniform and non-degenerate donor doping concentration of ND1. It is 1 into 10 to the power 18 per centimeter cube, and ND2, it is 10 to the power 15 per centimeter cube, corresponding to N plus N regions, and thermal voltage is given 25 millivolt. Ni, it is 1 into 10 to the power 10 per centimeter cube. Then what is the magnitude of built-in potential? Okay, so here we have to calculate internal built-in potential. It is, the formula is Vt ln Nd1 over Nd2. So we'll put here Vt is given 25 millivolt. So we'll put here it is 25 into 10 raised to power minus 3 ln Nd1, it is 10 to the power 18 per centimeter cube, and Nd2, it is 10 to the power 15 per centimeter cube. And when we solve it, so Vbi, it is 0.173 volt. What are graded semiconductors? Graded semiconductors are which have non-uniform doping. And due to non-uniform doping, some internal voltage, which is called as built-in potential, generates. As we can observe from here, right? Let me understand. This is a graded p-type semiconductor. Okay. At this position, hole concentration is greater than this position. This is position A, suppose, and this is position B. Okay. So at position A, we are taking voltage V1, and X is X1, and P is P1. P is hole concentration. At position B, we are taking V is V2, X is X2, and P is P2. When it is isolated semiconductor, then net current density is 0. Hence, drift plus diffusion current density is 0. Drift current density is PQ mu P into E. And diffusion current density is minus of Q into dP over dx. So PQ mu P into E, it is equal to Q into dP over dx. And electric field is minus of dV over dx. So it is P into minus of dP over mu P. It is equal to, so here minus dV into dP over mu P, it is Vt according to Einstein's equation. D by mu, it is equal to Vt. Vt is thermal voltage. So dP over P, it is equal to minus 1 over Vt into dV. When we integrate on both the sides, so it is P1 to P2 dP over P, it is equal to minus 1 over Vt, V1 to V2, it is equal to T, right? So the 1 over P is, its integration is ln P, P1 to P2 minus 1 over Vt, and it has integration of V2 minus V1. So ln P2 by P1, it is equal to minus 1 over Vt into V2 minus V1. So V2 minus V1, it is equal to Vt ln P1 by P2. So this is our expression of built-in potential, right? Built-in potential comes into the picture when there is a non-uniform doping. When there is a uniform doping, then P1 is equal to P2, and this voltage will be equal. Then in this case, V1 is equal to V2, and electric field, it is a built-in electric field here. And the same we can do into the graded n-type semiconductor. It is a graded n-type semiconductor where at the point A, electron concentration is greater than point B. So the net current density is 0 here, and J diffusion plus J drift, it is equal to 0. So N Q mu N into E plus Q into dN over dx, it is equal to 0. And when we solve as a similar manner, right, as we solved for the p-type semiconductor, and the expression comes as V2 minus V1, it is equal to minus of Vt ln N1 by N2. So here V2 minus V1 is negative, it means V1 is greater than V2. So based on this, these questions are of graded semiconductors. As we can see in this device, it is a n plus n semiconductor where ND1, it is 10 to the power 18, and ND2, it is 10 to the power 15. So so this is more doping concentration than this, right? That's why built-in potential is getting generated. So built-in potential, it is Vt ln 10 to the power 18 over 10 to the power 15, and we get our magnitude of Vt, it is 0.173 volt. So you can ask me any doubt if in these topics any doubt is there. Okay, so I am winding up this today's session. We meet in the next session.